All right, hi folks. I'm recording a video for MATH140 Section 1.6 on calculating limits. So in Section 1.5, discuss what a limit is and how to find one-sided limits and two-sided limits. Now we start to look at more direct ways of finding limits. First, let's go to some properties of limits. And so these properties are going to help us simplify limits. Now, in these properties, notice it says C is just a constant, so C is just a number. And here are a few of these properties. It says if I'm taking the limit as x approaches a of f of x plus g of x, I can really break this up and take the limit separately of f of x and g of x. Same thing if I have the limit of a constant times the function, I can really put that constant out in front and just take the limit of the function itself. So let's do a few examples. This is almost, you can think of this as like algebraic properties of limits. So the next slide just explains that when you take the limit of a sum, you can really break it up to be the sum of the limits. You know, in a sense, this is almost like a distributive law. It's almost like you're taking this limit process and distributing it both f of x and g of x separately. Let's do a couple of examples. So they're giving me this graph. They're going to ask me here to find these limits that involve both f of x and g of x. All right, let me look at the first one. It says the limit as x approaches negative 2 of f of x plus 5g of x. Well, the property I just mentioned allows you to take the limit separately of f of x, then take the limit separately of g of x. For that limit of g of x, I'll multiply it by 5 and then add the limit for f of x together, and that will be my final result. So let's do it on the next slide. All right, we're going to do part A here. First question is, what's the limit as x approaches negative 2 of f of x? Well, f of x is this pink graph, so they're asking me what's the limit as x approaches negative 2? Well, negative 2 is here, and let me approach negative 2 from the left side, and I want to see what happens to the y value. Well, if I'm approaching x equal negative 2 from the left side, there are some red dots on this graph, notice the y value is getting closer and closer to 1. I'm also noticing that at x equals negative 2, the value of the function jumps to a y value of 2. But remember, that doesn't matter for the limit, because for the limit process, I only allow x to get closer and closer to negative 2. So the answer for the limit as x approaches negative 2 for f of x is a y value. All right, let's do the same thing for g of x. All right, so now I'm going to be approaching x equals negative 2, but now I'm on the blue g of x curve. When I do that, you can see I'm moving down on this curve, and it looks like the y value is getting closer and closer to a y value of negative 1. All right, well, now that I know the limits for f of x and g of x, let me go ahead and go back to this problem that says take the limit of f of x. Well, I know that's going to be 1. The limit of g of x was negative 1, but I'm going to multiply it by 5. So that's 5 times negative 1. So, of course, this turned out to be 1 plus negative 5. So the answer to this is negative 4. And so I applied those properties to break this down into a simpler procedure because it allowed me to find the limits separately. All right, let's go to problem 2, part B, part B. Part B said, let me go back to part B just as a reminder. Part B said the limit as x approaches 1 for f of x and g of x. All right. Well, let's do the limit as x approaches 1 for g of x and see what happens. So I'm going to be approaching the x value of 1. And let me go from both the left side and the right side and see what happens for g of x. Well, when I approach x equal 1 from the left side, I'm putting these red dots. Notice the y value is getting closer and closer to negative 2. So the limit as x approaches 1 from the left side for g of x is negative 2. All right, now let me approach from the right side. We do this with a blue arrow. I'm going to approach x equal 1 from the right side. When I do that, I'm moving down on this blue curve. I'm drawing some dots here. Notice x is getting closer and closer to negative 1. But if you remember from section 1.5, there's no limit then. The limit doesn't exist because I end up with different values coming from the left and right. So the answer to part B does not exist. The limit for g of x does not exist. Okay, so again, you got to be careful that the only time a limit exists is if the left-sided limit results in the same value as the right-sided limit. All right, let's go to section 1C. This says, what's the limit as x approaches 2 for f of x divided by g of x? All right, well, remember there's a property that says you can break this up and take the limits separately of the top and the bottom. So let's go ahead and find the limit for f of x. This is as x approaches 2. So it looks like the limit as x approaches 2, we draw this on the diagram. Here's x equal 2, and it looks like as I'm approaching x equal 2, it looks like the y value here is a little hard to read from the graph, but I'm going to assume the y value is about 1.4 there. What's the limit for g of x as x approaches 2? Well, for g of x, I'm going to be on that blue line, and let me draw some blue dots. Here is x getting closer and closer to 2. I'll even come in from the other side, but notice the y value is approaching 0. So what we end up with is the limit as x approaches 2 of g of x is 0. So remember what we're going to do here. Let me just go back to those rules just as a reminder. So let me jump back a few slides. We're working on this rule at the very bottom. It says when you take the limit of f of x over g of x, you could take the limit separately for the top and bottom. If we do that for this example, we get into trouble because when I take the limit separately, top and bottom, so really what I'm going to do here is take the limit of f of x on top and also separately take the limit for g of x on the bottom. So when I do that, the limit of f of x we figured out was about 1.4, but the limit of g of x is 0, and of course I can't divide by 0. So the given limit here doesn't exist because in this case, the denominator approaches 0, and I can't divide by 0, of course. All right, so these are these properties of limits. And let's go ahead and do some examples. So let me pick one or two of these examples to do. And notice here on the top, they're giving me the values of the limit. So the limit as x approaches 2 of f of x is 1. The limit as x approaches 2 of g of x is negative 5. And the limit as x approaches 2 of a of x is 0. All right, let's do part A. So for part A, they want to know the limit as x approaches 2 of f of x plus 5g of x. Well, I'm going to really break this up and find the limit as x approaches 2 of f of x to begin with. But I'm told that's equal to 1. And then I'm going to take 5 times the limit of g of x, but the limit for g of x is negative 5. So this works out to be 1 plus negative 25, and you can see the answer here is going to be negative 24. Okay, let me do another example. But if we go down to the bottom, it's asking me the limit as x approaches 2 of g of x over h of x. Well, similar to what we did a few minutes ago, I'm going to go ahead and take the limit separately, top and bottom. Well, the limit of g of x is negative 5, but the limit of h of x is 0. So I end up here dividing by 0. That's why the answer is D. Of course, you remember that you cannot divide by 0. So that answer is D and E. Notice the WebAssign instructions say if an answer does not exist, enter your answer as the capital letters D and E in the answer box. All right, folks, we're going to talk about here a important limit property. It's called direct substitution. What it says is if f is a polynomial function, then when you take the limit as x approaches a, it's really going to just turn out to be the function evaluated at that number a. The reason that's the case is a polynomial function is always continuous. So there's not going to be any scenarios where the graph is going to have a gap or a jump or anything like that. We go back to the example we did a while ago where the limit did not exist. So you might remember when we did this example back here on slide 6, do you remember the limit here did not exist for g of x? Because we ended up getting a different answer for the limit coming from the left side versus the right side. But g of x here is not continuous. Continuous function, polynomial function was continuous. Continuous function has no gaps or jumps like this g of x is showing. A polynomial function is one that you can always trace out with a pencil without ever needing to lift your pencil up off the paper. So what it says is if the function is polynomial, then you really can just evaluate the function at that value, and we'll do an example in a second. Also, if the function is a rational function and a is in the domain, for example, a does not result in division by 0, you can then use the same property. Let's go to this example here. It says the limit as x approaches 3 of x squared plus 5. Well, x squared plus 5 is a continuous function. Let me draw x squared plus 5, just so you can get a sense. X squared plus 5, x squared is a parabola. So this graph would do something like this. The limit at x equals 3 is really going to end up being the value of the function at 3. Right? Because when I approach from the left side or the right side, I'm just going to end up with this same y value. And I can figure out the y value by just replacing x with 3 in the expression. And so the limit here turned out to be 14. Notice all we had to do here was direct substitution, meaning substitute the value of 3 into the function. All right, let's do a couple of examples here. And let me do the bottom example. Let's do both examples. Let me go to the top. The top, as long as u is in the domain of this function, which it is because you'll notice if u is -3, I'll be taking the square root of a positive number. So u equal -3 is in the domain of this function. So to work this out, really what I could do is just evaluate this function when u is -3. So I'm just going to replace u with -3 in this function and then work this out numerically. So if you work this out, this is going to be the square root -3 to the 4th, 81. And then that'll be plus -9 plus 9. So this is just going to be the square root of 81, which gives us the answer of 9. So I use direct substitution to evaluate this limit. The bottom example. The first thing I have to ask myself, is t equal 2 in the domain of this function? Well, to answer that, let me just check that if t equals 2, the denominator does not equal 0. So let me evaluate the denominator when t equals 2. That's 2 times 2 squared minus 3 times 2 plus 9. And if I work that out, 2 squared is 4. 2 times 4 is 8. Then it's 8 minus 6 plus 9. But that's 2 plus 9, so I think that's 11 in the denominator. So it's not 0. So that means t equal 2 is in the domain of this rational function. And that tells me I can just use direct substitution. So let me go to the top and replace t with 2 there. That's 2 to the 4th minus 7. 2 to the 4th is 16. That's 16 minus 7. 16 minus 7 is 9. So it looks like the answer to this is 9 over 11. Okay, again, we were able to just use direct substitution for these examples. All right. Here's another important property. Let me go to this example. You might notice I can't use direct substitution here. The reason I can't is if I let x equal 5, 5 is not in the domain of this rational function, because if I let x equal 5, on the bottom of the fraction, I'll have 5 subtract 5, which is 0. We can't let x equal 0 because we end up dividing by 0. But here's a property. It says down here at the bottom, it says if f of x equals g of x when x is not equal to a, then the limit as x approaches of f of a is really going to be the same as the limit as x approaches a of g of x, provided the limit exists. What this is trying to say is you can simplify the function first, take the limit after the simplification. So you can evaluate the limit for the simple function. Now, when I say simplify, you might be able to cancel out a common factor on the top and bottom of this example. So let's go ahead and do this example then using that property. Let me go to the top of this fraction, and I'm noticing for the top, I can factor x squared minus 9x plus 20 as x minus 4x minus 5. But notice what happens now, this x minus 5 cancels out. So now I could take the limit as x approaches 5 of just x minus 4. Notice now I can evaluate the limit because that denominator is gone, so I won't end up dividing by 0. And so this turned out to be 5 subtract 4, so the answer to this question is 1. So what I can do then before taking the limit is try to simplify the function and then take the limit after the simplification is done. That's what this property is telling me that I can do. Right? F of x is like the original function. G of x is the simplified function. And it's telling me the limit of f of x is going to be the same as the limit for g of x. All right, so let's do a few WebAssign examples here. And you're going to have to keep in mind the factoring rules that you know from algebra. If you're a little rusty on factoring, please go back to the pre-calculus review that's posted in Canvas and practice some of that factoring. We'll go to the top example here. And it turns out I cannot direct substitute x equal 3 in this example. The reason is I would end up dividing by 0. So instead, I'm going to try to do some factoring. All right, let me look at the top. I'm noticing that I can factor an x out on top. If I factor an x out on top, I end up with x times x minus 3. Let me try to factor the bottom as two binomials. All right, well, if I factor the bottom, you might notice I can rewrite it as x plus 1 times x minus 3. Remember, we're still taking the limit as x goes to 3. But now what I could do is make use of the fact that I have an x minus 3 both top and bottom, so I can cancel those out. And now this is the limit as x approaches 3 of the simpler function, which is just x over x plus 1. And now I can use direct substitution because I'm no longer in any danger of dividing by 0. So the answer here is 3 over 3 plus 1, Of course, that's 3 over 4. All right, let me go to the bottom example, same idea. Again, I can't use direct substitution because if I let x equal 4, I end up dividing by 0. So instead, I'm going to try to factor the top. Let me write the top as 2 binomials, so the top looks like x. Well, it turned out I can't factor the top. So I'm trying to factor the top, but I can't. So it looks like there's no way I can't factor it. I mean, I can't factor it to cancel out the x minus 4 is what I meant to say. I could factor the top as x minus 2, x minus 5. But if I do that, that really doesn't help me because I'm not able to cancel out that x minus 4 on the bottom. So there's no way for me to simplify this and cancel out the x minus 4. So the answer here is D and E. Notice here in the yellow box it says if no cancellation is possible, then the limit may not exist, and the answer is then D and E. All right, let's go and do maybe a couple more examples. All right, let's take a look at this one. This one's a little tricky. It says evaluate the limit if it exists. Now notice I can't directly substitute h equals 0 because there's an h in the denominator. I would be dividing by 0, so that's not going to work. But how about if I try to see if I can cancel out that h in the denominator? Well, to do that, let me multiply out the numerator. So when you see -5 plus h squared, really think of that as a FOIL multiplication. So I'm going to multiply it out as -5 plus h times -5 plus h. So if I do that multiplication on the top, that's going to be 25 minus 10h plus h squared. I'm just doing a FOIL multiplication on the top. And I'm also going to bring with me this subtract 25 as well over h. Well, notice the 25s cancel out on the top because I have a 25 subtract 25. So those cancel out. The other thing I'm going to do now is let me factor out an h from the top of this fraction. Because now I can factor out an h from this remaining expression. So when I do that, that's going to leave me with -10 plus h on top, and I still have h on the bottom. But the good news is, if I have an h on top and an h on bottom, I can cancel out that h. So let me cancel out the h's. Now I'm left with the limit as h approaches 0 of -10 plus h. But now I can use direct substitution. So this is going to be -10 plus 0. Of course, that gives me the answer. So the answer to this question turned out to be -10. So again, I was able to cancel out the h in the denominator, but first I had to expand the numerator using a FOIL kind of multiplication. All right, let's go to the last slide. And here are some more examples. All right, well, the bottom example is going to be very similar to what we just did on slide 16. For this bottom example, I can't let h approach 0 because I'll end up dividing by 0. So what I'm going to do is multiply out the x plus h to the third. Remember, that really means take x plus h times itself 3 times. So multiply that all out, and then try to factor out an h from the numerator. If that happens, if you're able to factor out an h from the numerator, use that to cancel out the h in the denominator, then take the limit as h approaches 0 once you've canceled out that h in the denominator. All right, let me go to the top example. And for the top example, again, I can't let x equal -2 for direct substitution. That would end up resulting in division by 0. But let me try to do a factoring experiment. So this is going to be the limit as x approaches -2. Now I'm noticing on the top I can factor as x plus 2 times x minus 2. And on the bottom, I'm sorry, x plus 2 times x plus 2. On the bottom, when I see x squared, x to the 4 minus 16, you may notice that's the difference of 2 squares. So I can write that as x squared plus 4 times x squared minus 4. Again, this is going back to factoring from algebra. This is the difference of 2 squares. But once I factor that, I'm noticing x squared minus 4 can factor again as x plus 2 times x minus 2. So I'm factoring this x squared minus 4 as this x plus 2, x minus 2. All right, now let me go ahead and write out what I have left. I have x squared plus 4, and then I have an x plus 2 and an x minus 2. And I'm noticing there's an x plus 2 that I can cancel out, top and bottom. So let me do that. I'm going to cancel out one of these x plus 2's. Now let me see if I can go ahead and use direct substitution. Well, it turns out -2 is in the domain of this function, right? I'm not going to end up dividing by 0 anymore because I canceled out that x plus 2 factor. So now I'm going to use direct substitution. All right, well, this is going to be -2 plus 2 on top. And then this is going to be -2 squared plus 4 on the bottom. And a -2 subtract 2 also. All right, well, this bottom parenthesis here is an 8 times a -4. But notice the top of this fraction is a 0. So what I end up with here is 0 over -32. And so the answer here is 0. So the limit turns out to be 0 in this example. Okay, folks, hope this is helpful to get you started in the WebAssign homework for Section 1.6.